Dear students, in this class, now we are going to theorem. The theorem states that suppose A is a subset of R. F is defined from A to 1, comma, which is uniformly continuous on A. Then if xn, secant xn is Cauchy in A, then secant f of xn is also Cauchy. Then secant f of xn is Cauchy in where? In R. A is a subset of R. F is uniformly continuous on A, where F is defined from A to R. Then if secant xn is a Cauchy sequence in A, then f of xn is a Cauchy sequence in R. Means the uniform continuous image of a Cauchy sequence is nothing but Cauchy. How to prove this one? So let secant xn is given, or secant xn is Cauchy in R. Cauchy in A. Secant xn is Cauchy in A means let epsilon is positive. Choose delta positive, delta greater than 0, such that modulus of x minus u less than delta. Since f is uniformly continuous, let epsilon is positive, choose delta positive, such that modulus of x minus u delta less than delta. If modulus of x minus u less than delta, then modulus of f of x minus f of u strictly less than epsilon. Why? Because f is uniformly continuous. This given f from A to R is uniformly continuous on A. So for every epsilon is positive, there exists delta positive with a modulus of x minus u less than delta, then modulus of f of x minus f of u less than epsilon for all x comma u fall in A. Okay, but what is xn? Since xn is a Cauchy sequence in A, that means modulus of xn minus xm less than delta for all n comma m greater than or equals k, where k is fall in n. Agree. If modulus of xn, what is xn and xm? Where xn and xm are chosen from where? A itself. Since xn is Cauchy, modulus of xn minus xm less than delta for all n comma m greater than or equals k. So, but if modulus of x minus u less than delta, then according to this argument, for all epsilon positive, then such that modulus of f of xn minus f of xm should strictly less than epsilon for all n comma m greater than or equals k fall in n. Why? Because of the light of this argument. Okay. When modulus of f of xn minus x of xm less than epsilon, this means secant f of xn is Cauchy. Why? Because that is from the definition of a Cauchy sequence. Okay, since f is uniformly continuous, we know that when mod x minus u less than delta for all x comma u fall in A, mod f of x minus f of u less than epsilon. If xn is a Cauchy sequence in A, then we know that for delta is positive, mod xn minus xn less than delta. So by using this argument, this should implies mod f of xn minus f of xn less than epsilon for all epsilon positive. So that means f of xn is a Cauchy sequence. Okay. Now we are going to an important theorem, which is a well-known theorem. The theorem is known as continuous extension theorem. That is very important. The theorem is known as continuous extension theorem. What is continuous extension theorem? The theorem states that, statement of the theorem states that a function f is uniformly continuous on open interval AB if and only if it can be defined, means f is defined at the n points of this interval a and b such that the extended function is continuous, or extended function is continuous on where? Continuous on closed interval. So this is the continuous extension theorem. There exists an extended function. If f is continuous, f is uniformly continuous on open interval AB, if and only if the function is defined at the n points a and b such that the extended function is continuous on closed interval AB. So this is continuous extension theorem. How to prove? Its proof is, come to the necessary arguments. It is immediate. First, suppose that f is uniformly continuous. Suppose that this f can be defined. First, the first inclusion is, suppose the function f is defined. Assume f is defined at the n points of the interval, open interval AB, means at the n points a and b, such that the extended function is continuous on closed interval AB. Extended function, that's our first assumption. F is defined at the n points a and b, such that, the second part, such that the extended function is continuous on AB. Extended function is continuous on AB means, when extended function is continuous on AB means f is continuous on closed interval AB. But the continuity on a closed interval should implies the uniform continuity. Therefore, f is uniformly continuous on closed interval AB. The continuity on closed interval AB should implies the uniform continuity on such interval. So f is uniformly continuous on closed interval AB. This implies f is uniformly continuous on open interval AB. Why? F is uniformly continuous on open interval AB, since open interval AB is a subset of closed interval AB. So clearly f is uniformly continuous on open interval AB. Why? Because open interval AB is nothing but a subset of closed interval AB. Okay. Since f is uniformly continuous on closed interval AB, so first we define f at the n points of this interval a and b in such a way that that extended function is continuous on closed AB. That means f is continuous on closed AB. But on the closed interval, continuity should imply uniform continuity. So f is uniformly continuous on closed AB. Therefore, since closed AB, so open AB is a part of closed AB, so f is uniformly continuous on open interval AB. So first part is finished. Okay. Now come to the reverse inclusion. Reversely assume that f is uniformly continuous on open interval AB. F is uniformly continuous. F is uniformly continuous on open interval AB. So this is our assumption. Let's suppose let sequence xn, let a sequence xn be a sequence in open interval AB. Sequence xn be a sequence in open interval AB such that sequence xn converges to E. Sequence xn converges to E. Since sequence xn converges, means sequence xn is Cauchy. Sequence xn is a Cauchy sequence. Sequence xn is a Cauchy sequence means f of xn is also a Cauchy sequence. Why? Because our previous theorem, that is the uniform continuous image of a Cauchy sequence is always Cauchy. Means when xn is Cauchy, f from a to r is uniformly continuous on A, which is a part of R, then f of xn is Cauchy on R. So f of xn is Cauchy. f of xn is a Cauchy sequence. Okay, f of xn is a Cauchy sequence, then that means this f of xn is convergent. Okay, f of xn is convergent. F of xn convergent means limit f of xn exists. That means limit f of xn exists. Limit f of xn exists. So let limit f of xn equals L. Let limit f of xn equals L. Now let un, u of n, un, not u of n, un be any sequence, be a sequence in open interval A, such that un also converges to A. Xn is a sequence in AB which xn converges in A, and un is again a sequence in AB, then un also converges to A. Then what about limit un minus xn? Limit un minus xn equals limit un minus limit xn. It is limit un minus limit xn equals a minus a. Limit xn converges to a as well as un converges to a. So limit un equals a and limit xn equals a. So limit un minus xn equals 0 itself. Okay. Limit un minus xn equals 0. But what is f? F is uniformly continuous on AB. Xn and un are any two sequences in open interval AB which converges to A in such a way that limit un minus xn equals 0. So f is uniformly continuous on AB. Since f is uniformly continuous on AB, then we have limit f of un minus f of xn. Limit f of un minus f of xn equals 0. Why? We know that un and xn are any two sequences in open interval AB with the limit un minus xn equals 0. Since f is uniformly continuous on open interval AB, so limit f of un minus f of xn equals 0. Now, what is f of un? F of un equals f of un minus f of xn plus f of xn. Okay, you can add f of xn and minus f of xn simultaneously. So what is limit f of xn? That implies limit f of un. Limit f of un equals limit of f of un minus f of xn plus limit f of xn plus limit f of xn. Okay. This goes to 0. Why? Because of this argument. So that means limit f of un equals limit f of xn. But what is limit f of xn? Let limit f of xn equals L. So limit f of un is also L itself. Okay. Thus we get some value L for every sequence converges to A. If xn converges to A, limit f of xn is L. If un converges to A, then we got limit f of un is L. Means we get some value L for every sequence which converges to A. So you define f of A equals C. For every sequence, so we get some value L. We get some value L for some convergent sequence to A. Now define f of A equals L. F of A equals L. Then f is continuous. Define f of A equals L. Then f is continuous. F is continuous at A. Okay, f is continuous at A. Similarly, we can prove that f is continuous at B. When f is continuous at A and f is continuous at B, then surely f is continuous at or continuous on closed interval A. Okay, so first there exists some value L, which is for every sequence there exists some value L for every sequence converges to A. So you can define f of A equals A. Means f is continuous at A. Similarly, you can prove f is continuous at B. So f is continuous on closed interval AB. So this is the continuous extension theorem. Enough.